is many things. Nikki, if you can advance the slide, there you go. So we know that science is content knowledge, the body of knowledge about the world around us and how it works. But it's also the inquiry process. So actually, doing the experiments, discovering things and adding to that content knowledge. And then it's also the quest for solutions. So why even do science? And so that social context is important too. And so whenever any scientist is thinking about how, what sorts of things to investigate, it really encompasses all three of these things. And so what students should think about is really this what we call the triad of science. So thinking about, what's already known and what interests them, where their interests lie and how that might affect the world around them. So with Chuck's example earlier, is hairspray harming my plants? That has a social context. If you're doing your hair by your plants, is there going to be an effect on those plants? And then also with the inquiry process, how are they going to go about doing that? What resources are available to them, either right with them, or how can they connect to someone with those resources? And so what I always tell students, we're really lucky in Pittsburgh that we have some great people all around us in Pitt, CMU, Duquesne, and all of these great areas of higher ed, but also technology. And there's so much going on in Pittsburgh. But also, if it isn't even working in a lab, it's connecting with scientists around who are looking to help. So within the inquiry process, it doesn't necessarily have to be super complicated, but there are resources available to help students as well. and yeah, so
okay.
The last thing I just wanted to say on that is really getting students to think about all three of those things for their project.
Okay. Hi, I'm Janet Vukatich. Those of you who don't know me, I am a member of the Scientific Review Committee. Also, I co-chair the Senior Engineering Division for judging at PRECEF, and I've also co-chaired at ICEF. And I also go out usually in the fall and talk to students. I do a workshop for students. Mostly I do middle school, but I've also done some high schools, including Jan Waldeck's high school. And the first question that students always ask me is, how do I know what to do? How do I pick a topic? How do I decide what my science fair project is going to be about? And the first thing I tell them is choose a topic that interests you. Don't choose something because your teacher said it was a good idea or your parents thought that that was a good way to go. Find something that interests you. And I tell kids, particularly in middle school, this is really a way to do them. Look at some of the things they do or after school, an extracurricular activity that they enjoy. Music is really a good one. There's a lot of science related to music. Sports, we get a lot of sports projects. Any outdoor activities like gardening or camping or things like that, that will really are things that you are already involved in that obviously interest you because you are spending time out of school to do them. So find something that interests you, or find an issue that affects your life, like the hairspray young lady. Something that we have a lot of students, particularly in high school, who start their biological research because one of their parents or a relative has a problem that they need to resolve. Or find just a topic that just fascinates you. We get students who look at space travel because that topic really just absolutely fascinates them. And those are the three things that they should be thinking about when they're trying to select a topic. Then they need to determine if the project is feasible. Okay, what does that mean? We are on a fairly short timeline. Okay, so do you have enough time to complete the project? If a project's going to require 9 months of intense lab work, you might not have enough time. If it requires to have a major lab available and you don't have access to a major lab, you don't have the resources available. So you need to determine if the project is feasible. And that's what I tell the kids. Don't try and do something that requires you to be in a lab in the city when you have and you live out in rural Indiana County, and there's no way that you can get into a lab. So you have to be careful. You can look at ICEF abstracts and even some of our pre-CEF abstracts to get ideas. They're almost all available online. You can search the ICEF abstracts way back and look for stuff in your area of interest and find out things that might give you an idea of where you can go from here. Next, Nikki. What not to do. Use a canned project from a website like Science Buddies. This particularly happens in middle school, and it's where kids go to find ideas. It's okay to do that if you put your own special twist on a project, but just picking up something that's a canned project, and we see this all the time in the SRC, we'll get a research plan that is obviously cut and pasted from Science Buddies. That's not a good thing to do. The kid isn't learning anything, and they're not very competitive when they do stuff like that. Again, don't pick a project based on your parental or teacher influence necessarily. It's okay to say to a teacher or your parent, I want to do this, what do you think? But it shouldn't come the other way. The teacher or parent shouldn't say, you ought to go do this. And don't pick a topic that doesn't interest you, okay? We get students who you can tell when you're interviewing them that they really have absolutely no interest in this project that they did. And the only reason they did it was to get a grade. So we don't want that to happen. A student needs to be enthusiastic about what they're doing. Okay, need to plan ahead. The first thing that a student needs to do is create a research plan. Once they've picked an idea, they need to create a research plan. And these are the items that need to be in their research plan. This is things that the Scientific Review Committee, the SRC, look for. They look for having a rationale. Why am I doing this? You need a research question, a hypothesis, or an engineering goal, if they're an engineering project. They need to have a procedure. They need to identify that they've thought about the risk and safety of their project. They need to have a little bit about how they're going to analyze the data. And they need to have a bibliography. Now, the two things that are in highlight there are the two most important things. We will generally be able to pass a project on review if they have at least a procedure and a bibliography. Okay, if they don't have either one of those, we're going to send it back to you and to the student to add those things. So make sure that your students have at least a procedure and a bibliography when they create a research plan. Okay, Becky?
So I just want to kind of touch on some things that go along with the scientific process and kind of build on the points that Janet just made. But one of the main things that I like to caution with students is it's really important to form these habits of scientific thinking if they haven't already. So within the scientific method, it's important to keep skepticism. So, don't decide what the outcome is going to be before you gather the results. Keep an open mind and think about all the alternatives and what sorts of things could impact an experiment. And rationalism is important too. So you want objective empirical evidence and really differentiate between fact and opinion. So it all comes down to forming these habits while you're working through the scientific method.
Yes. Okay, the first step is to form a hypothesis or statement of your problem. So your hypothesis should state what you believe will happen as a result of your experiment. Your problem statement for engineering should state the problem that you're trying to solve. This is a big problem with engineering projects. And since I co-chair engineering, and we often get students who are doing an engineering project who have a hypothesis. That's not really the point of engineering projects. Engineering projects should solve problems. That's what engineers do. And I try and emphasize this when I talk to the students. So there is a differentiation, and the rubrics that we use for a science project versus an engineering project are different based upon the goals of those two kinds of projects. The research that a student does before they start their actual research, you know, when you go out and look at what's been done in the past, should inform the development of your hypothesis, your problem statement. In other words, they should go out and look at what's been done before and what the next steps are going to be in order to they can develop their own hypothesis or their own problem statement. So a student who is, for instance, in engineering, building something to solve a problem should go out and see what other things have been done to solve that same problem, and to see the point is of their research is to see if they can do it better or do it cheaper or do it in a faster time period. Okay.
So it's, you know, might be obvious to us, but, you know, thinking about controls at a time and designing the experiment with controls is really important. So you want to make sure that when you're designing your experiment, you're measuring one single variable, and that all other conditions are controlled. So everything else about your control versus your experimental should be the same, so that the only difference is what it is that you're testing. And so from a judge's perspective, looking at whether students have thought that through, how are they controlling their experiment is really important. Okay, and again, we know what controlled experiments are, but with students, I always, you know, make sure, again, thinking through what's going to be the manipulated variable, what's the controlled variable, what's the responding variable then, and then are there any uncontrolled variables that can impact results. And so making sure that the students think these through when they're designing their experiments, and then also predicting the outcomes of their results are really important and help to make a sound project. And so I just mentioned making predictions. This is a step I think a lot of students skip, but I think really helps when thinking through the process. And so even before conducting your experiment and analyzing your results, it's important to make a prediction of what you think will happen based on your hypothesis. So it's an if-then statement. So if my hypothesis is true and I do this experiment the way I explained, then this is the result I expect. And so that might seem intuitive to some, but I think it really helps when students write that out. And then, you know, I make clear with the students also that your results do not have to match your prediction. And in fact, a lot of times they don't, and that is perfectly great. But it really helps when it comes time to analyze your results to see, what did I predict? Did it actually match up? Yeah. And then when it comes time to analyzing the results, it's important to think about quantitative data over qualitative, thinking about how to graphically and statistically show whether there are differences in your experimental subjects, and then really thinking about, is any variability with the manipulated variable greater than variability due to chance or other variables? So again, that's where controls come in, and really looking at, you know, what was manipulated and is any difference seen there really due to the experiment that you did. And then when it comes time to draw conclusions, you want to make sure that the conclusions are based on the interpreted data. So don't, this again comes into those habits, good scientific habits to have. Really just base your conclusions on the data that you get. You want to identify if your hypothesis is consistent And remember that your conclusions are only as good as the data is accurate. So coming back to experimental design, if you design a good sound experiment, then you can trust your conclusions. If there's a ton of variability, then those conclusions won't be as concrete. And then if you need to revise your hypothesis, redesign the experiment, and conduct further studies, as we all know, science is an ongoing process. So even if, you know, the experiment they designed in the time that they had for this science fair, you know, led them to a point, there's always more to do or other questions to ask. So it's always important for students to be thinking about big picture and what else could be done with that experiment.
Yeah, there are lots of resources out there. The first place you should always go is to the Precept Student Teacher Handbook. That will hook you up to other places, including the ICEF rules and regulations and a couple of other places. It gives you a starting place. There is a NASA site that helps you how to do a science fair project, which is a good place to steer students to. It's a pretty good procedural kind of thing. A place called Using Statistics in Science Fair Projects. And then there's a bunch of places where you can find the engineering design process, which is, by the way, always an iterative process. It's never just one and done. There's always something you can make better. Okay, I think we're done, Nikki.